this is the equation what we have derived yesterday. Clear? So and S is unknown to us, and we have written S as a Taylor series extension. Okay, as an identity minus I by 4 sigma mu delta. Okay, so for the infinitesimal Lorentz transformations. Okay, so let's substitute this S here. Yes. So what is our S inverse? So S inverse is simply change in sign I by 4, because for a unitary transformation S diagonal is equal to S inverse. Okay. Clear?
Yes, sir.
Okay. So let's substitute S in this very equation. And what is our lambda? Okay, so I should have put lambda also. So lambda mu we wrote as eta mu plus delta omega. Clear? So this is the infinitesimal Lorentz transformation. For that we have expanded S. Okay. We have expanded S in Taylor series expansion. Clear?
Yes.
So this is these are the results what we have obtained yesterday. Clear? Any question regarding this? No question? Okay. So let's substitute this S, lambda and S inverse in this very equation. Let me call this as equation 1. Okay, so you have your own numbering. Okay. So what is our LHS? So let me take LHS, lambda mu gamma nu. So let's write for this lambda. What's lambda? Eta plus delta omega. Clear? So how I will write? Eta mu plus delta omega mu. Is it visible?
Sir.
Gamma nu. Okay. So how much is that? So it is, let's multiply. Eta mu gamma nu plus delta omega mu gamma nu. Yeah, I have yesterday I have told one wrong thing. I will tell you. I will correct that in a moment. Okay, I will tell you in a moment. So what this object is? So nu will get contracted, is it? Okay, so nu is contracted, and this nu will be replaced by mu. Okay, so you will be having gamma mu here plus. So let's write it as delta omega mu gamma mu. Okay, yesterday I have told you something wrong. Okay. So we have this gamma nu plus gamma mu is equal to twice eta mu, is it? So this eta mu is a matrix. It's a 4 by 4 matrix defined in Minkowski space. Clear?
Yes, sir.
Mu and nu specify those indices. Let's say mu equal to 0, mu equal to 1, mu equal to 2, mu equal to 3. Is it? From 0 to 3. These are actually space-time indices. Clear? The indice is defined in space-time. But this gamma matrix itself is not defined in the space-time. Okay, it's a matrix, and this matrix is defined in what we call the Sipner space. Okay, the space defined by the Hilbert space of the particle. Let's say if you are having an electron spin. Okay, so let me pause here. I have told actually some wrong thing here. Okay, so let's say if you are having a spin half particle. So your Hilbert space of an electron with spin half comprises of two parts. One is the Hilbert space defining the spatial variation of the wave function. Okay, only the spatial components of the wave function is defined, and the part of the Hilbert space defined as the spin component of the electron. Clear? If you don't consider, let's say, spin of the electron, you will define it by simply the wave function. Let's say you are having an electron in 1s orbital. So what is the wave function? E raised power minus r kind of thing, is it? You don't associate spin to that. Clear? Now if you write it with including the spin, so what you have to do? You multiply it by the spin wave function, like this thing. So you start with an electron, let's say in okay, so 100. So it is something root of pi a cube e raised to power minus r by a. A is the Bohr mass. Clear? Is that true?
Yes, sir.
Everybody knows this formula. So this is a wave function defined where? In coordinate space. If you don't consider the electron. Sorry, if you don't consider the spin. So this is the 1s wave function. Wave function of electron. Okay, now if I consider the spin as well, so I will write the wave function as 100, okay, tensor product of the spin component. Forget about this tensor product, you multiply simply it by the, let me write some phi which describes the spin. Okay, you got it? Got it? So this phi s lies in a Hilbert, two-dimensional Hilbert space. How many components you are having for spin? 2. So that means you can describe it by two linearly independent vectors. For example, you can have spin up or spin down. Clear? So you are having only these two possibilities. So you are having a Hilbert space corresponding to this spin as a two-dimensional space. You can ignore, let's say, if you are in a magnetic field, it is the spin of the particle which responds to the magnetic field. There will be splitting of the energy lines, is it? So you restrict yourself to only the two-dimensional Hilbert space. Clear? So we call this space as a spin space of the electron. Clear? Got it? So in this very spin space, you are having those Pauli spin matrices. Sigma x, sigma y, and sigma z. So this set of Pauli matrices are defined within where? Two-dimensional Hilbert space defining the spin. Clear? And you can assign, let's say, let's assume this defined as be the spin up component. So let's assume this defined as be. So this are two column vector spin down state. Clear? So we call these as spinors. Okay, let's say this is a spinor. That means a spin wave function corresponding to, let's say, spin up. Okay, and a spin wave function corresponding to the spin down. Okay, and they exist where? In a two-dimensional Hilbert space. Got it? Okay. In a similar way, okay, now you have an idea of a spinor. Okay, you can think this spinor is associated with an intrinsic angular momentum of the particle. So we are considering, let's say, here a two-dimensional particle. Clear? Sorry, we are considering a two-dimensional Hilbert space because you are having only two components of the spin here. Clear? Got it? So you are having a spinor like this in 1, 0 or 0, 1. Call them as a spinor, and within this very space, you define these Pauli spin matrices. Because you define Pauli spin matrices coming from the angular momentum comment, you know how to do those things. Clear? Okay. Similarly, in this very case, since we have a Dirac equation that has this psi as a wave function, and it's a 4 component. Clear? So you can think this exists in, let's assume in an intrinsic, let's separate out the special part of the wave function from its intrinsic angular momentum part. Clear? Then I can say this spinor, this 4 component, what I call as a spinor for the time being, so it exists in some Hilbert space. Clear? So in that Hilbert space, these are the 4x4 matrices. You got my, like you are having a special index here. X is a special index. But sigma itself is a matrix, is it? And this matrix is defined in this space. Similarly, these gammas are defined in the spinor space. These are matrices in a spinor space. But as the, let's say gamma 0 is a component corresponding to mu equal to 0. Samashavan? These gammas can be large matrices, they can be smaller matrices. Clear? And then you need, okay, so now this eta is entirely defined where? In the Minkowski space. It's not defined where? In the spinor space. This eta comes from these indices. Samashavan? Okay, so what you need to put? You put an identity here. Clear? Samashavan, and this identity is defined where? In the spinor space. Samashavan? Got it? Everybody followed it? Huh? Okay. So now let me apply a unitary transformation. Okay, so let's apply the unitary transformation. So if I apply the unitary transformation, where I am applying? Am I applying on an index or this gamma? I am applying it on gamma. Clear? You got my point? So that means this unitary transformation will not affect this identity. So this unitary transformation will not affect this gamma. You had yesterday like this, u eta mu nu and u inverse, is it? Yesterday, no, but this is not a diagonal matrix. Clear? Since this is already a diagonal, this is not diagonal. It is actually like this thing. Eta mu nu identity u inverse. So eta mu nu will come out. Because this is a unitary matrix only defined for where? Sifner matrices. Clear? And you are having an identity here. So then you are having u identity u inverse. So what this is equal to? 1. So that means this anti-commutation relation will be satisfied. Got it? Otherwise it is not true. Samajh aaya? Got it? Any question? Okay, good. So this was a wrong point yesterday I have told you. Okay. Okay, so let me simplify this object a little bit. Okay, so let me write it as gamma mu plus. So let me write this thing in terms of, let me write like this thing, G, okay. So what we can do, so I want an different kind of index. Okay, so okay, so for the time, let's keep it as such. Let's keep it as such. Let's take the RHS, RHS of the equation. Take the RHS, then we can compare. Okay, so let's take the RHS. So what is our RHS? So it is S inverse gamma mu S. How much is that? What is S inverse? Everybody is following? Huh? Okay, good. So we are having 1. It is identity. It's not 1 actually. It's identity. I by 4. That we write sigma alpha beta delta omega alpha beta. Then you are having this gamma mu. Okay, so then I can write my alpha beta. Okay, so now let's write it. So what is it equal to? The first element will be gamma mu. Clear? So gamma. Okay, so let me multiply it for you people first, step by step. Delta omega alpha beta gamma mu like this thing, then you have I minus. Okay, so let's write. So it is gamma mu. Okay, then so this multiplied by this object 1, so it is plus I by 4. So let me write sigma alpha beta delta omega alpha beta gamma mu. Okay, then you are having this object multiplying this gamma mu, so it is minus I by 4. You need to take care of the order of these matrices, sigma alpha beta delta omega alpha beta, plus another term which is order of delta omega square. Clear? So this multiplied by this is, what is the order? Delta omega square, because you are having delta omega and delta omega. It is delta omega square, and in omega is what?
Infinite.
Delta omega is very small, infinitesimal. Huh? Okay. So let's write it. Okay. So what you have, so that's equal to gamma mu plus I by 4. Okay, so you can take out delta omega alpha beta because it's a number, huh? But this is not a number, it's a matrix. Huh? This is a matrix, this is a matrix. Huh? You are having a matrix. We know because we know this is an unknown quantity for us. Okay, this is actually a matrix. If you see, the elements of this very object is a matrix. Clear? But if I take this delta omega alpha beta, delta omega is actually a matrix, 4 by 4 matrix, an antisymmetric matrix. Clear? But if I take delta omega alpha beta element, so that will be a number. समझ आवा? Clear? So you can take delta omega alpha beta common. So let me write. So what is there? So you are having sigma alpha beta gamma mu minus gamma mu sigma alpha beta. Okay? So clear? Okay, so now this has to be equal to LHS. So this has to be equal to LHS. So what is that? Gamma mu plus delta omega mu nu gamma mu. Clear? Is it? So this cancels with this thing. Okay, now what you are having, since omegas are free, these are simply arbitrary numbers. Clear? It is an infinitesimal number, it's a completely arbitrary. I want to remove it from this as well. I want to take this delta omega mu nu in this form, delta omega alpha beta. Clear? Got it? Okay, so let's write it. Okay, so let me put it in this way. So this very object. So let me write G mu alpha delta omega alpha mu gamma. Can I write it? Can I write it? So this alpha gets contracted. Clear? So this alpha gets contracted. What mu comes here? Clear? Okay. So you can write it as G mu alpha. Okay. So delta omega. You can take this nu up and lower down this nu like this thing. Nu gamma. Can I write it? So when you are having in this very form A mu B mu, you can write it same as A mu B mu. Okay? Clear? So can I write this as G mu alpha delta omega? Since nu is a dummy index, I can write it as delta alpha beta gamma beta. Can I write it? Can I write it? Any problem? Okay, good. So you can have G mu alpha gamma beta, this object multiplied by delta omega alpha beta. Okay? So now you cannot arbitrarily cancel this delta omega alpha beta with what? This. Why? The reason being, look, this object is antisymmetric in alpha beta. Clear? And you don't know what is the symmetry property of this object. Clear? You need to properly symmetrize or antisymmetrize this very quantity. Okay, so this is antisymmetric in alpha and beta. So that means this object must be what? You need to, okay, so antisymmetrize in alpha and beta. Clear? Everybody follows it? So if this is antisymmetric in alpha beta, you need to antisymmetrize this in alpha and beta. Okay, if this is symmetric in, let's say, alpha and beta, you need to symmetrize this object here because you have these two indices, the same kind of indices there. Clear? Okay. So let's try it. So I can put it this way. So G mu alpha gamma beta minus G mu. You don't need to take. Why this G? So we are using eta. We are using eta instead of G here. So let me write. Don't do anything with mu. What are the indices? Alpha and beta. You put alpha, gamma, beta. Then minus eta mu. What you are antisymmetry? Alpha and beta. So interchange the two. Like this thing. Gamma, alpha. Divided by 2 then you are having delta omega alpha beta. Clear? Got it? So you are anti-symmetrizing this set of indices alpha and beta. Okay, now you can cancel out this delta omega alpha beta with this. Clear? So you can take it out. So what you get, and two. So okay, so you can have like this thing. So what you get, eta mu alpha gamma beta minus eta mu beta gamma alpha, that is equal to, anybody, I by 2. Okay, so it's a commutator between sigma alpha beta and gamma mu. So is this a commutator? Is this a commutator between sigma alpha beta? Clear? Or in other words, everybody followed it? Huh? I'm going step by step because I'm slowly, so that you will understand how to manipulate these objects. Okay? Or I can write this way, or sigma alpha beta gamma mu, I can write it as, okay, twice I. Okay, so 2 comes here, I will be down, so then you take I up, it is minus, I will take this minus out, it is something eta mu beta gamma alpha minus, so I will put a minus eta mu. Okay, so this is an identity. If this is satisfied, then I can say we are having a Dirac equation as a covariant under Lorentz transformations. Clear? Got it? So what is unknown? We don't know sigma. What is sigma alpha beta? So that means we need to sigma alpha beta satisfies this equation. Okay? I need to figure out what sigma alpha beta is so that this equation is satisfied. Okay? So let's make a guess. Because looks, your hand sigma is having a commutation with a gamma. Clear? And you see these etas come because of the anti-commutation of gamma. Clear? Now look here how we can guess. You are having gamma here, is it? You are having gamma and gamma. Clear? And you know these etas come from where? If I make an anti-commutation between gamma matrices, gamma nu plus gamma nu is equal to twice eta. Clear? So that means these etas must be generated from where? Anti-commutation between the gamma matrices. So how many gamma matrices are there in the commutator? Only one. And you are having sigma alpha beta, is it? So in this commutator you are having only one gamma. So that means this sigma alpha beta must be written in terms of the gamma matrices. So that if I make the commutator between these or anti-commutator between the gamma matrix, I will generate etas. Clear? So you can see. Okay, so let's make a guess. So we use, okay, let's have a smart guess. Huh? Okay, so we write sigma alpha beta as I by 2 gamma alpha, this commutator. Okay, and let's check whether this satisfies that equation or not. Okay, so let's calculate the commutator between. Okay, so check. Okay, so we'll take this commutator sigma alpha beta and gamma mu. So what is sigma alpha beta I have taken? So I assume this sigma alpha beta satisfies that equation. Let me check it. Right? So let me calculate the commutator. So it is I by 2. Okay, so it is gamma alpha. So it is, let me write I by 2 gamma alpha gamma beta minus gamma beta gamma. So it is like this thing. So you can take I by 2 out minus gamma beta gamma alpha, and then you are, sorry, I'll put this. Clear? So let's take, so I by 2 gamma alpha gamma beta, gamma mu. Okay, then you are having minus I by 2 gamma beta, gamma alpha. Gamma. Okay? Clear? So just A plus B and C. Clear? So it is AC and BC. Everybody followed it? Okay, good. So let's call this as 1 after whatsoever. So let's swallow this very object first. So we will keep this result here. So what is the commutator? Gamma alpha, gamma beta, gamma mu. Okay, how I will write it? Gamma alpha, gamma beta, gamma mu minus gamma mu, gamma alpha, gamma beta. Okay. So what I will do? Okay. So I will displace these. I will displace this gamma mu on this side. Clear? So that term will cancel with this very term. I will do nothing with this thing. What I am trying to do, I will just displace it here by using the commutation between these two things. Clear? Okay. So what is our commutation? So let me write it here. So you are having, let's say, gamma alpha, gamma beta. So that you can write as twice eta alpha beta minus gamma beta gamma alpha. Is this the way? So just this plus this is equal to this thing. Clear? Okay, so let's write it. So it is gamma alpha. So what is this gamma mu? So you can write it as now, Munir sir, just tell me, twice eta mu beta. Clear? Minus gamma mu gamma beta. Minus, keep this there. Got it? So you should know how to do the algebra of these gamma matrices, okay? Because it will be very useful when we will do the trace of these gamma matrices. Okay. So now let's write it. So it is. So you are having now twice gamma alpha eta mu beta minus gamma alpha gamma mu gamma beta minus gamma mu gamma alpha gamma beta. Okay, so let's write it. Let's keep it as such. Okay, minus. So let's do it this for this very term. Okay, so what you are having twice mu alpha, then you are having minus gamma beta gamma alpha. Clear? And you are having then minus gamma mu, okay, gamma alpha gamma beta. Clear? So I use it this. Okay, just when you interchange the two, you will get what? This eta. Okay? So what you have? So you are having twice gamma alpha. So let me write it this way. Twice, okay, this way. Eta mu beta gamma alpha minus, so 1 is so you are having a gamma beta here as well. This gamma beta. Okay? So then you are having eta mu alpha gamma beta. Clear? So minus and minuses plus gamma, sorry, why this is, so this is gamma mu, so this is gamma mu, gamma, so it is gamma mu, gamma alpha, gamma beta minus gamma mu, and this cancels. Okay? Got it? So what you got from the very first term? Okay, so let me write. From the very first term, you are having this gamma alpha, gamma beta, gamma mu. What is that equal to? Twice eta mu beta gamma alpha minus eta mu alpha gamma beta. Clear? Now let's look at the second commutator. So therefore I am having second commutator gamma beta, gamma alpha, gamma mu. Is it? So that this is the second commutator. Okay? Now look here, in the second commutator you are having in the first one alpha beta, is it? In the second commutator what you are having? That means alpha and beta are interchanged. Clear? So you just interchange in this result what? Alpha and beta. So that's equal to twice eta mu. So it means it is simply interchange of what? alpha beta, so it is alpha gamma, just tell me, beta minus, so it is like this. Okay, eta mu beta gamma. Clear? So now 1 by 2 is sitting outside, and there is in the second term the minus sign. So therefore I am having sigma alpha beta gamma mu. That's equal to I by 2, and you take 2 common from each, so it is 2. So what remains there? So eta mu beta gamma alpha minus eta mu alpha gamma beta, and in the second term there is a minus sign, is it? So it will be minus eta mu alpha gamma beta plus eta mu beta gamma. Clear? So this 2 and 2 cancels, this and this, these are twice, so it is simply, and you take this minus out, minus twice I eta mu alpha gamma beta minus eta mu beta gamma alpha. Clear? Now tell me, is this equation satisfied? Is this equation satisfied? So that means we are having a correct case. So this is a correct case. So we have figured out what? Sigma. So now if sigma has this form, then our Dirac equation is coherent. Clear? Samajh aaya? Okay. So therefore we can write we have therefore this S of lambda, that's equal to identity minus I by 4, okay, sigma mu nu delta omega nu. So how much is that? Identity minus I by 4, okay. What this is? Sigma mu nu, it's I divided by 2, okay, gamma mu, gamma nu, okay, delta omega. So how much is it? So it is plus 1 by 8. Now you can check this sigma alpha beta. So everybody has written this thing? Huh? Now you can check this sigma alpha beta is antisymmetric. So if you take sigma alpha beta, so that's actually minus sigma beta alpha. So you change beta and alpha, what you will get? Commutator is antisymmetric in interchange of the operators. Clear? Got it? Everybody followed it? But what we have constructed? We have constructed the infinitesimal this S matrix, Lorentz transformation matrix, that will act on Sipner psi. Clear? Because S is a prescription which will take, okay, so what is S? So if you are given for an observer psi of X, you act it by S of lambda, what it yields me? A transformer wave function. Clear? So S is a matrix that will act on Sipners. Got it? Samajh Shaman? Okay. So now let's construct the finite case. I mean the finite transformation. So how to do that? Okay, for that matter, what I will do, so since this is an infinitesimal quantity, this delta omega, you can construct it from some finite quantity omega. Omega is a parameter, okay? Omega is a parameter, clear? It's a free number, okay? So you can take, divide it by n, okay? N tends to infinity such that, okay? So n tends to infinity such that n delta omega is fixed. Clear? But if you see delta omega mu nu, that it is a tensor, rank 2 tensor. Clear? It's a matrix. Got it? What I will do, so I will write this delta omega mu nu as this way. So I will write it as omega mu nu. Okay, so let me write it in this way. Delta omega some I yi is a matrix. Okay, let's assume we are in the n-dimensional space-time, so it's an n by m square matrix. Clear? And its elements are, it's an antisymmetric matrix like this thing. So you can put mu nu. So let me tell you what it means. So I will simply write it as I mu nu. Why I is some matrix, clear? And with each element of that matrix, you are multiplying delta omega, so that this gets p. Clear? So if you remember last time when we have calculated the infinitesimal Lorentz transformation simple, and we arrived at this delta omega mu nu. You remember it? What was that? 0 minus beta and 0. You remember it? You remember it? Okay, so what you can do, you can take minus beta out. So what remains there? 0, 1, 1, 0. So you can call this as what? Your I. Clear? So I means it's a matrix purely out of numbers. Huh? Clear? And you take this parameter out. Clear? Okay. So this I can write now as omega by n I mu. Okay? Clear? So we will take an example in a moment. There you will see. Okay. Anybody? Any question? Okay, good. So how to do now the finite transformation? Okay. So finite transformation means, okay, let's take the finite transformation. Okay. So how to do it? You apply, let's say, 1 minus I by 4 sigma mu nu delta omega mu nu. Okay. How many times? N times. Clear? So that means you are taking the this object. Okay. So you apply this on n time and take n tends to infinity. Okay, and n tends to infinity. So then you will get what? What you will get? The finite transformation. So you are adding the infinitesimal small elements to get a finite element. Clear? Got it? Okay. So now what I will write? Therefore the finite s of lambda, that's equal to limit of n tends to infinity. Okay. 1 minus I by 4. Okay. So I will write like this thing. Psi prime sum x prime. So acting on what? Sum x. Okay. So you will get sigma mu nu. What is delta omega mu nu? It's now omega by n I mu nu. Okay, raised power n. Clear? Everybody followed it? So this factor is n times. I have put what? Delta omega mu nu as omega by n times I mu nu. Okay? So what that is? Anybody? So it is exponential of minus I by 4. It is something, this entire object by n, x by n. Clear? 1 minus I x by n. Clear? Got it? Okay, so that will be e raised power minus ix. Okay, so what is that? So it is sigma mu nu omega I mu nu. Okay, so that's equal to e raised power minus I by 4 sigma mu nu. Let me put it as omega nu. So why omega mu nu is this will be the finite. Okay. Clear? Got it? So we usually put it as, okay, you can put it as theta and so on. Okay, so let's try to get the interpretation of this thing. So what we have arrived at. So what we have, okay, so let me repeat it. So you started with a Dirac equation, okay? Let me write it. Minus m psi of x is equal to 0. Clear? And you want this equation to be covariant under Lorentz transformation. That implies, okay, this psi must transform under Lorentz transformation this way. E raised power Okay, let me write that as S of lambda psi of x, where, okay, so that's equal to e raised to power minus I by 4 sigma mu nu. I will write delta omega. So it is a finite delta, huh? So it's not the infinitesimal, it is finite here. So I will be using this delta omega. Clear? You got it? So that means if you want your equation to be invariant under Lorentz transformation, then the Sipners must transform in this way. Okay? The wave function, that is the solution of this this Dirac equation, under Lorentz transformation, it should have this kind of transformation property. It should transform in this way. This S of lambda, this object acting on psi of x gives you. So this we have proved. Okay? So this is how this S should go. Okay? And you are having, we need to interpret now this sigma mu nu. What is it? Okay? Gamma mu, gamma nu. Clear? Got it? So now let's take the interpretation of this sigma mu nu first. Any question till now? Any question? Okay. So let's take, let me take, okay, since it is antisymmetric matrix, sigma 0, 0 is equal to 0, that's equal to sigma 1, 1 is equal to sigma 2, 2, it is equal to, since you are having sigma mu nu as minus sigma nu. So that means you need to consider only the 6 elements of this very matrix. Clear? Okay. So let's take, okay, now if you see, this is, okay, if you see from this very equation, so you are having, yesterday we have said the generator of the transformation. Clear? So if you remember from the yesterday's lecture, so we wrote this psi of t, okay, so e raised for minus I h t by h cross acting on this psi of 0. Clear? So that means this very object is what? Generator of the time translation. So now if you see, since t is a parameter, this object is a parameter. It's simply the parameter. It will specify the elements of this delta omega mu nu will give you the amount of, let's say, the boost along one direction, the other direction, or the amount of rotation in any plane. Clear? Got it? We have seen it. Delta, let's say delta omega 0, 1, that is the boost along x direction with velocity vx, let's say, or let's say delta omega 1, 2, that will give me the rotation in xy plane. Let's say that is amount of the angle phi. Clear? So that means it will simply quantify how much rotation you are specifying in a given plane, whether it is in px plane or xy plane and so on. Clear? Now what is what makes it to do? What is an operator that will do it? Okay, so it is sigma. Like you are making a translation here by an amount of t, is it? From 0 to t, clear? So it is the operator h which helps us to do so. So if delta omega is the amount of, let's say, rotation in any plane, so what is the operator corresponding to that? Sigma mu nu. So that means I can say this sigma mu nu is some kind of generator which will generate me the Sipner transformation. Got it? So it will simply generate a Sipner transformation. What does that mean? It will simply take a Sipner from one, okay, from one coordinate to the another coordinate. Clear? So that means sigma mu nu has an interpretation of a generator. Got it? The way you are having the angular momentum, if you know, so let's say if you are having angular momentum, e raised for minus I j dot theta by h cross. Let's say jz and theta. Clear? Jz is the total angular momentum. It can be spin angular momentum. It can be orbital angular momentum. What does it do? So what this operator is doing, it is simply rotating your wave function in xy plane or about z direction. Clear? So I can say this jz is an operator, or jz is a generator for the rotations. Clear? Got it? So in other words, since we are in the four-dimensional Minkowski space-time, so this sigma mu nu, since it is having only 6 independent parameters, it's antisymmetric, it's having only 6 independent parameters. So that means it must specify, it will specify me a generator for the boosts, it will specify me the generator of rotationals. Okay, so let's check it. So let's take sigma 0 1 element. So then you will see it. Okay. So what is sigma 0 1? It's I by 2, gamma 0 and gamma 1. So let's evaluate it. It's I by 2. Okay? Clear?
Yes, sir.
Okay, so if I take sigma 0 1, okay, so first let's calculate. So it is gamma 0, gamma 1 minus gamma 1, gamma 0. Can anyone tell me what gamma 0 is? Gamma 0 is 1, 0, 0, minus 1. Clear? So let's take it as, okay. So these are two-dimensional matrices. So these are the identity matrices. 2 by 2, 2 by 2. So what is gamma 1? 0, sigma 1, sigma 1, 0. Or minus sigma 1. It's minus sigma 1. Minus 0, sigma 1, minus sigma 1, 0. Sigma 1 is a polyspin matrix. 1, 0. So identity minus identity. So you get to multiply. So multiply. So this will be 0. Is it? Then you are having sigma 1. Then you are having sigma 1, 0. Minus you are having 0. Then minus sigma 1. What you are having? Sigma minus sigma 1 and 0. So what you are having? Just add. So 2 will. So it will be simply like this thing. I times 0. Okay. Sigma 1. Sigma 1, 0. Clear? Clear? So what it gives me? It's actually sigma matrix. Clear? So if you see, it's actually alpha matrix. Is it? So much more?
Yes, sir.
It's an alpha matrix. So it is I times alpha 1. Remember it?
Yes, sir.
Okay, so now let's check it. Let's put it here. So let's take that very combination. So you are having sigma mu nu delta omega mu nu. Okay? So if I take now boost along x direction, clear? Okay. So let me take, so you so let's take boost along x direction. Okay? So what does that mean? Delta omega. So what I need to consider? Delta omega 0 1. Is that true?
Yes, sir.
This will represent me the boost parameter along x. How much is that? Beta. Is it? Teacher? Clear?
Yes, sir.
Huh?
Yes, sir. 0 beta.
Is it true? Okay, good. So now let's try therefore this psi prime x prime. So that's equal to, so it is e raised power minus I by 4. So I am having sigma mu nu delta omega mu nu acting on psi of x. So let's write it. It's e raised power minus I by 4. Since I am considering boost only, is it? So much, so that means 0 1th element. So what I will be having? So let me write delta omega 0 1. So you are having here 0 1. Clear? So then you are having also this element 1 0 delta omega 1 0 because they are the same things. Clear? So you can be, okay, I know if you are having delta omega 0 1 as non-zero term, delta 1 0 is also what? Non-zero term. Clear? You got it? Oh, so much, because it's an antisymmetric matrix. Now look here, so you are having e raised power minus I by 4, sigma 0 1, I will write it as 0 1, okay? So this I will put as plus sigma, okay, so when I interchange this 1 0, you will get a minus sign, is it?
Yes, sir.
And interchange this, you will get a minus sign. What you will ultimate is plus 0 1. Okay. So how many are they? There are 2. So it is e raised to power minus I by 2 sigma 0 1 delta omega 0 1 psi of x. Clear? So it's like this. So this is beta. If you write it in the down, that is minus. Okay, so what that is equal to? E raised to power minus I by 2. What is sigma 0 1? We are just I times alpha. Clear? So it is I times alpha 1. And what this is? Let's write it as
Beta.
let me put it as a delta beta, small change in velocity. Clear? So you can put as beta. Forget about it. So beta is a v by c. So now if you see what you are having, it is the same kind of objective. E raised power minus I j dot theta, like this thing, minus I j z theta by h cross. Clear? Since we are using h cross equal to 1, so what you are having? So that means this I alpha by 2. Clear? So compare with this thing, e raised power minus I j z theta. Compare with this thing. Theta is a parameter. What is parameter here? Beta. Is it? Okay. So put minus I here. What remains there? I alpha by 2. So that means this alpha is having. So alpha is making simply it is simply a boost generator along x direction. In other words, I times alpha gives you the boost direction along x direction. If you take now, let's say sigma 0 2, similarly sigma 0 3, you will get I alpha 2, okay, and you will get here I alpha 3. Clear? So in other words, you will see sigma 0 1, okay, sigma 0 2, sorry, sigma 0 1, sigma 0 2, sigma 0 3. They will be actually the generators corresponding to boosts along x direction, y direction, and z direction. Clear? Got it? Okay. Now let's take the other components. Let's try to understand the other components. Okay. You followed it? You followed it. So in other words, you can write this object simply as e raised for simply alpha by 2 beta psi of x, because I and I is what? What I and I is?
Minus 1.
That is plus. Okay, I and minus I is plus. Clear? So you can put it this way. Clear? So now let's take the other case. Let's assume the rotation. Okay, so let's take this object. It's sigma 1 2 elemental. So that is I by 2. Okay, gamma 1, gamma 2. So let's take this very element. Clear? So how much time is remaining? So work it out. Gamma 1, gamma 2 minus gamma 2, gamma 1. Okay, so I by 2. What is gamma 1? 0. Sigma 1 minus sigma 1, 0. What is gamma 2? 0. Sigma 2 minus sigma 2, 0. Minus 0. Sigma 2 minus sigma 2, 0. Okay, and then you are having 0. Sigma 1 minus sigma 1, 0. Okay, so let's write this product. So it is, okay, tell me. So you are having minus sigma 1, sigma 2, then you are having 0 here, clear? Then you are having 0 here, then you are having minus sigma 1, sigma 2, then minus, so you are having minus sigma 2, sigma 1, 0, 0, then you are having minus sigma 2, sigma 1. So how much is that? Okay. So let's write it. It is I by 2. So it is simply minus, I will take out. So it's minus sigma 1, sigma 2, minus sigma 2, sigma 1, 0, 0, minus sigma 1, sigma 2, sigma 1. Clear? Got it? So now tell me, what is the commutator between sigma x and sigma y? It is twice I sigma z. Is that true? Okay. So that's equal to I by 2 minus twice I sigma 3 0, 0 minus sigma 3. You can take minus 2i out, what remains there? So I and minus I is plus, 2 and 2 will cancel out. So it's simply what? Sigma 3, 0, 0, sigma. So that is the sigma 1, 2 gives you the poly third component of the spin matrix. Clear? Got it? समझ आओ? Okay. Similarly, you can have sigma 2, 3 as sigma 1. Sigma 1, 2 will give you the rotation in xy plane. So how you do that? With sigma 3, clear? As Z matrix, clear? Okay. So in general, you can write like this thing. If you are having sigma ij, you can put it this way. Sigma I, sigma j minus sigma j, sigma I 0, 0, sigma I, sigma j minus sigma j, sigma I. So how much is that? So it is twice I. Sorry, so you should. Okay, twice I. No.
Sigma
So it is minus times like this thing. Minus times this thing. So then you are having I by 2 here. So 2i. So you will be having minus 2i. It will be like this thing. Epsilon I j k sigma k 0 0 epsilon I j k sigma k. Where sigma k is the kth polyspin matrix. Okay, so you can write this as, so remember this very formula, sigma k, where this sigma k is equal to sigma k 0 0 sigma. Clear? Got it? Got it? Samashama? So remember this very relation. It is epsilon I j k sigma. Okay. So now let's take the rotation in xy plane. Okay. Assume a rotation in xy plane through an angle phi. Let's say delta phi. Clear? And let's say through an angle phi. Okay. So what does that mean? This delta 1 2 has to be equal to this phi. Clear? So that's equal to minus delta omega 2 1. Because delta gives you this omega gives you the parameters of boosts and rotations. Okay? So therefore I can write this as psi prime x prime is equal to e raised power minus I by 4. So now we are considering for the components of delta omega as 1 2 components, is it? So what I will write it as sigma 1 2 delta omega 1 2 plus sigma 2 1 delta omega 2 1 acting on psi of x. Everybody is following it? So I am considering only one kind of parameter here. That's why, because you are having an anti-symmetry, so you need to take two terms. Huh? Okay, so let's write it as, so it is e raised power I by 4, so it minus I by 4. So this is twice, because you can change, so it is sigma 1 2 minus, so it is minus delta omega 1 2. Minus and minus plus, so it becomes the same term. Clear? Okay? So it is sigma 1 2. Now tell me what is sigma 1 2? What is sigma 1 2? It is sigma z. Clear? This one.
Sir. Sigma.
This is? So this is sigma 3. Clear? So let me write for the time being sigma 1 2. So what is delta omega 1 2? It is phi. So psi of x. So it is simply equal to e raised power minus I by 2 sigma 1 2 phi psi of x. So in other words, sigma 1 2 is a generator corresponding to rotation in xy plane. Clear? That means you are defining a rotation about zx but in xy plane. Clear? Got it? So sigma 1 2 is that generator. But if you remember from your quantum mechanics, it's actually the jz or the sigma z component is giving you the rotation where? In xy plane. So that generates the rotation in xy plane. So that's why you see the sigma 1 2 turns out to be sigma z
Is it? Although it's a 4-dimensional matrix, so it turns out to be what? Sigma z. Clear? So you can write it as e raised power, okay, minus I by 2 sigma z phi psi r. So in general, that means this sigma ij, it will be the generator for rotationist in ijth plane. Clear? Got it? So now you got the idea what this sigma is doing? Got the idea? Okay, good. So we'll take a more